Now that we've learned about how to plot polar coordinates and about converting polar coordinates with rectangular coordinates, we're going to move on to looking at some of the graphs of polar equations. So not just point by point, but putting it all together. What do some of these graphs look like? These are learning targets 4 and 5, using polar symmetry tests to determine if a graph is symmetric about the x-axis, y-axis, or origin, and identifying points where max r values occur on the graph of a polar equation. So we're going to start off first off by just talking about how our calculator needs to be set up to be able to view polar mode, because this is new to us. So to analyze, we're going to start off with finding the max r value. Those max r values occur at the point on the curve that is the max distance from the pole. Remember, that pole was that replacement for the origin, that center point on our polar graph. And those points are where the max r values occur. So whatever is furthest away, so you're looking for the extremes from the pole, how far away do they go, and where are those points? You've got two options to solve. If we were to leave our calculators in the modes they are in now, we would use this first set of directions, changing the polar equation into rectangular equation by making your r your y and your theta your x, graphing the equation, and determining the max r values, which would now be, since we replaced r with y, the maximum y values, the maximum distance away from the x-axis. And then find all the values of theta where this occurs. What that would mean if you're in this first example, or in this first set of directions, is that since you replace theta with x, you're going to need that theta to go in between 0 and 360 so that you can see a whole unit circle worth. And now that you replace that theta with x, when you set your window to be able to use this first method, you'd have to set the window so that your x went from 0 to 360. The second option, which is the one that we're going to use as we go through the examples today, is to put the calculator into polar mode. And this is a new thing for you, and it's under the mode of your calculator, and I'll show it to you here in a second. Graph the equation and determine the max r value, which is the maximum distance the graph is from the pole. So you are looking at it as an actual polar equation, and you're looking for the extremes from that point. So if you're looking at a graph, you're looking for where did it go furthest around there. Well, this one is furthest away from that center point, so those would be the points we were looking for. And then finding all the values where that occurs, which you can use trace to do. I will be going through it with the second option in polar mode. However, if you feel that this first mode might be better for you, feel free to try it out and see what you like better. Every year there are at least a few students who enjoy that first method a little bit better. Okay, so here's what you need to do to set up. Under the mode section of your calculator, and I've got a screenshot here for you, you need it to say all of the things mine say, and most of them will be the same. If you've got your calculator in radians, you need to set it to degrees, because we're going to use our window in degrees. It's easier to recognize angles in degrees. And then your calculator is in func mode right now. That's function mode, and that's the mode of what we've been dealing with our whole entire math careers up until this point, and that's the normal XY axis we're used to. If you look across that row, you see there are three other options. The option we want to choose today is pole, for polar. And we will also later in the year use parametric, so you have that to look forward to. That's PAR. So for right now, set it to degree mode and polar mode. And then go up to your window. Your window is going to look a little differently now than it did before, because you're going to have thetas to set, x's, and y's to set. Your theta are the angles you want to plug in. We're going to go from 0 to 360 by 1 so that we look at every degree on our unit circle. Then the x and the y. The x is really that r, that polar axis. How much of that polar axis do you want to see? The typical graphs we've been looking at have gone from -5 to 5, so go ahead and set it up like that. The y, they're really talking on the polar graph again. What do you want to see? We want this polar graph to be the same size, same dimensions, top and bottom, because if you use a radius of 5, it needs to go up to at least 5. So go ahead and set the y -5 to 5 as well. Once you have the settings set up like this, we're going to go ahead and move on to our first example, which asks us to identify the points in the interval 0 to 2 pi. Notice both 0 and 2 pi are included, so we need to make sure we include both if we end up with that answer, where the max R values occur in the polar equation. So you're going to graph R equals 3 cosine of 2 theta. I bet some of you are asking, where do I get R equals? Well, that's going to be your Y equals. If you hit that button in polar mode, you'll see that R equals comes up instead of Y equals. And now when you type the X button in your calculator, you're going to get a theta instead of X. So go ahead and type it in and graph it. And what you should see, so in my Y equals, I would have typed R1 as 3 cosine of 2 theta. What you should see is a graph that looks like this. So we're looking at our polar We're looking at our polar graph now. This is our polar axis. So imagine those circles drawn around here in those graphs that we've been dealing with these last several days. So here's my pole. I've noticed that I have 4 different points around my graph that are the furthest distance away from that pole. And they lie along the axis, so it should make it pretty easy for us to find. The first one looks like it's at 1, 2, 3 as that max R value, 3. We can use trace to verify. When you trace this time, you're going to be tracing with your thetas. You'll notice when you first hit trace, you'll get this first point. Theta is 0, and your x is 3, and y is 0. So you end up on trace this very first point being here. Once you have one of those points, you're going to try to find the next one. I'm not going to be mean and give you anything that's not on our unit circle. Okay, so try out some of the values on our unit circle. Try 30, you'll see it's not one of those maximum points. 45, it's not one of those maximum points. 60 is not one of those maximum points. But when you trace to 90 for theta, you should get one of the maximum points, 90 degrees, which is our pi over 2 if we're making a list in radians like it asked us to. So we've got 0, we've got pi over 2, 0, 90 degrees. Once you determine how they are separated, so this is a difference of 90 degrees, then they're going to continue in that pattern for the rest of the time. So once you find the first 2, whatever that difference is, keep adding that on until you get to the 360 or 2 pi that we need to get to. So if you keep tracing, the next one you should see is at 180 degrees, then 270 degrees, and then 360 degrees. Which would be all of the quadrantals, pi, 3 pi over 2, and 2 pi, as our locations for our max R value of 3. You'll notice that they don't necessarily go in order. What looks like 0 on the axis was 0 this time, but what looks like 90 may not be 90. What looks like 180 may not be the theta of 180, because it's all about what R values you get out. So you really need to pay attention to the trace on your graph when you're looking. Okay, example 2 is 2 plus 2 cosine. If I plot that in my y equals, I'm going to replace my R1 with 2 plus 2 cosine. You'll see that the graph looks different than the graph of our number 1. It looks a little bit different. And this time it looks like there's really only one maximum R value. So keep in mind we're still looking for the place that is the furthest away from that pole. And so here I've got a point that's very close to my pole. The furthest distance away is this right hand point that looks like it's 1, 2, 3, 4 away. I'm going to use that point. I'm going to use trace. And it happens at theta equals 0. That's my first location. So my max R value is 4. That's the furthest away I get. It happens at 0. Then I need to continue to look to find the next one. Trace your unit circle angles. And what you'll notice when you trace is that you just work your way around this lovely dimpled, kind of looks like a Pac-Man. You work your way around it until you get all the way back, and that's at 360. So your next value isn't until 360. So my only 2 locations for this one are 0 and 2 pi. Example 3. Go ahead and replace your R1 and graph 4 sine of 3 theta. Again, it looks a little different than the others. This time we've got 3 little fan blades here. And when we look at it, it's hard to tell how far away the 2 in those quadrants are. It's hard to see how far away we are over here and over here. However, these graphs are all going to have, when they have extremes, they're going to be that same difference away. And it's easy to see the one down here at the bottom, which is 1, 2, 3, 4 away from that pole. Okay, so I know my max R value is 4 because that's how far down I went in that graph. When I go to trace, the first location that I find one of those maximums is 30 degrees. Okay, that's pi over 6 in radians. That's the first location I see, and that's where my trace point is here on this graph. You're going to continue to go through your values. And so you're going to trace to 45, and you won't have one of those extremes. You're going to trace to 60, and you won't have an extreme. And you're going to keep tracing, and the next one you're going to find is at 90 degrees, or pi over 2. And just like we did in that first list, once you find the first 2, then that interval stays consistent for the remainder of the graphs. So this is a 60-degree interval. 60 degrees later is 150, then 210, then 270, then 330. Okay, so I should end up with that many more. If you trace, all of those points should end up on one of these outskirts. Now you notice that there are 6 points in my list, and there are only 3 points on my graph. If you pay attention when this graph graphed, remember when it's graphing, it draws that lovely little line up on the right-hand corner to say, I'm thinking, I'm graphing. And so if you pay attention to that little line, when this one graphed, it completed this whole curve, but then it kept thinking for a while. You couldn't do anything still for a while. And that's because this graph, with our theta from 0 to 360, actually traced over this graph twice. So it did the first graph, and that's what you saw, but then it kept thinking because it kept doing the graph and repeating back over itself. That's where our final 3 answers come in between that 0 and 2 pi. Convert yourself to radians, so I've got 5 pi over 6, I've got 7 pi over 6, 3 pi over 2, and 11 pi over 6. So I have a list of 6 different places where that max R value of 4 occurs. Just one last thing I want to point out, when these are not on the axis, you'll notice that you do not get a 4 as these values. You got a 2 and a 3.464. That's because our calculator is still graphing this, is still thinking about this as an XY pair. Your R is really the hypotenuse of that XY triangle. Okay, that's your R distance that you rotated through instead. So if you wanted to check to make sure that this was the max R value of 4, you could use the Pythagorean theorem, and 4 squared should equal your x squared plus y squared. So when you don't see that 4, when it doesn't fall on a quadrant, or when you don't see that max R value, you can use the Pythagorean theorem to verify that you are in fact at that max R value at that hypotenuse. Okay, that was part 1 of today's notes. Part 2 of today's notes is all about symmetry. Oops, back up. There are 3 types of symmetry we're going to look at, and this is different than the symmetry we talked about in our other functions with being even or odd. It's a little bit different. We're going to talk about 3 types of symmetry for polar graphs. They're symmetric about the x-axis, symmetric about the y-axis, or symmetric about the origin. We drew these points way back when we were talking about symmetry to begin with. About the x-axis would mean if you've got a point in the first quadrant and you reflect over the x-axis, that point should be reflected down in that 4th quadrant. If I'm thinking about this in polar values, that's a positive r, positive theta to get to the first quadrant point. But I have two different ways I can get to that second or that fourth quadrant point. Either positive r, negative theta, opening down, or negative r, opening backwards, and then pi minus theta. So a whole pi minus theta to get back. Kind of repeat this process with the rest of them. For the y-axis, my point in my first quadrant, r theta, would be reflected into the second quadrant, which would be a point negative r, negative theta, because I'm going clockwise, or positive r and pi minus the theta, so pi less than theta, or theta less than pi. About the origin, that's when you rotate 180 degrees. So that's when if I have a point in the first quadrant, I need that point in the third quadrant so that if I flip this upside down, it would look the same. So my r theta in the first quadrant is going to be negative r, positive theta, in the third, or positive r and a whole pi plus theta. So you have several different options for those other quadrant angles, and that's how we're going to do our test when we go to test these. So if you're testing for symmetry about the x-axis, you're going to replace that r theta value with either r negative theta or negative r pi minus theta, which are coming straight from this graph that we just drew. If you're testing about the y-axis, you're going to replace r theta with negative r negative theta or r pi minus theta. And if you're testing about the origin, you're going to replace that r theta with negative r theta or r pi plus theta. Just as a side note on this, you can usually check with the first replacement, the r negative theta, negative r positive theta. It's easiest to check for that first thing. However, if it doesn't work, you still have to try the backup. If one of those two options works, it is symmetric. So sometimes this first option won't work, the easy option won't work, you're going to have to default to the harder option, which if it does work would mean it is symmetric. Okay, so for these examples we're going to graph the polar equation to see if the graph is symmetric about the x or y axis or the origin. Then we're going to use the symmetry test to prove the symmetry. So I've already pre-graphed examples 4, 5, and 6. One quick hint for the symmetry test, you may need to remember the odd, even, or sum and difference identities. And I know it's been a while since we did that, so you might want to dig out your trig identity sheet so that you can see those odd, even, and sum and difference identities. So when I graph example 4, the first thing I say is, well, it sure looks like it's symmetric about the y-axis. So I'm going to say that as my guess. And what that means is I need to check to make sure that I'm right. So to check, we do one of those substitutions. So I'm going to plug in negative r, negative theta. So that's going to give me negative r equals 4 sine 3 times negative theta. Okay, and then I simplify. Negative 3 theta is now in my sign. And this is where I use the odd, even identities. Okay, so we default to the odd, even identities. And that says that the sine of a negative angle equals negative sine of the angle. Okay, so I'm going to take this negative from inside the sign, and I'm going to bring it as a multiplier outside the sign. And that's going to get me negative 4 sine of 3 theta equal to negative r. What I want to prove is that this equals the original. Well, if I divide both sides by negative 1, what happens? Those negatives cancel out, and I end up with r equals 4 sine of 3 theta. So I end up back with my original equation, which proves that it's symmetric about the y-axis. Go ahead and graph number 5, which I've already done. Number 5 gives you 1 plus 2 cosine of theta. And this graph looks different even than the rest of the ones we've seen. Okay, so we end up with a graph that looks like this. Again, we're checking for symmetry. Well, this one for me looks like it's symmetric about the x-axis. Okay, so we're going to check to see if it's symmetric about the x-axis. We're going to replace r theta by r negative theta, that easy replacement. So my r stays r, my theta now becomes negative theta. Again, when I have those negatives, we're going to default to the odd-even identities, which say that the cosine of a negative angle is the same as the cosine of a positive angle. Well, what that means is I can just replace this with the cosine of positive theta, and now I end up back at my original equation, which means that this is symmetric about the x-axis. Okay, last example for the day, example 6. Cosine of 3 cosine of 2 theta. If you graph, you should get this lovely flower-looking petal deal here. It looks like it has 4 different fan spokes here, and it looks like it's symmetric about the x-axis. You can kind of cut it down, the x-axis, the y-axis, and it even looks symmetric about the origin. If you were to rotate it 180 degrees, it should look exactly the same. Oop, little past. It should look exactly the same as how it did looking forward, which it does. So if I rotate that 180 degrees, I still get the same thing. So I'm going to check to make sure it's all 3. This looks like x-axis, y-axis, and origin, which means I have to do 3 checks, which is kind of a bummer, but that's the way the cookie crumbles. So we're going to start off with the x-axis. We're going to do that simple replacement, r negative theta. So I'm going to say, okay, r equals 3 cosine of 2 times negative theta. We just talked about that cosine identity where the negative angle was the same as the positive angle. So this check for the x-axis should be pretty fast. All you do is use that odd-even identity to take out that negative, and you've already checked. So we know it's x-axis. Then we check the y-axis. Okay, so we're going to try that simple substitution, which is negative r, negative theta. Negative r equals 3 cosine of 2 times negative theta. Well, we know that that negative inside the cosine using odd even becomes a positive. And what happens is we do not get back to our original equation because that r is negative and I've got no negative to cancel out on the other side. Since that substitution didn't work, we have to try the other substitution, because if one of them does, then it's true. So we do this other substitution, r pi minus theta. So I substitute r with r and theta with pi minus theta. Notice I'm using parentheses because I replaced one term with 2 terms. I'm going to go ahead and I'm going to distribute the 2. So I have 2 pi minus 2 theta. And here I have a difference inside of that cosine. So I need to use the sum and difference identities. Okay, so look up those sum and difference identities. When I use that identity, I'm going to get 3 times cosine of 2 pi, cosine of 2 theta, plus sine of 2 pi, sine of 2 theta. Now I have to evaluate 2 pi. Well, 2 pi is 0 degrees. That's the point 1, 0. Cosine is 1. Sine is 0. So cosine of 2 pi is going to be a 1 times cosine of 2 theta. And sine of 2 theta is going to be a 0 times sine of 2 theta. When you simplify that, 1 times cosine is cosine. 0 times sine is going to cancel out. So I end up with 3 cosine of 2 theta. So my r equals 3 cosine of 2 theta, and I've proven that I'm back to my original. The last one we have to check is about the origin. And I'll tell you right now, Once you find one that doesn't work, you might want to just default to using that second one, because when you run into the situation where it's all three, then you usually have to default to that second one on at least one or two of them. So we're going to go ahead and just plug in that second substitution, r pi plus theta. So I'm going to have r equals 3 cosine 2 pi plus theta. We're going to repeat this process where we distribute 2 pi plus 2 theta. And then we use the sum and difference identities. So it's going to be cosine of 2 pi cosine of 2 theta minus sine of 2 pi, sine of 2 theta. Doesn't really matter what order they go in because it's multiplication. And again, sine of 2 pi was 0. And cosine of 2 pi was 1. And when it all simplifies out, you're going to end up with 3 cosine of 2 theta. So you have proven that it is also symmetric about the origin. So we're going to say this is symmetric about all three. Okay, so our final answer is that it's symmetric about all three. And that's it for today's notes.